In this unit, we're going to be looking at some of the basics involving lenses and mirrors. We're only going to be talking about curved optics, not plane mirrors, and we're going to do this fairly quickly. So there's more details here than we're going to cover, but this will just give us the basics. So first part, we're going to do a few terms just to make sure we have everything defined correctly. Mostly we're going to be talking about lenses in this chapter. So what is a lens? It's something that refracts light rays in order to form an image. So we're going to be looking at two basic types of lenses. We're going to be looking at convex, which if you look at a convex lens, it's really formed from two arcs of a circle. So the shaded area in the middle of those two overlapping circles, that would be what forms a convex lens. Now the size of the arc or the curvature there will define how the lens bends light. And that's true for the concave lens as well. Instead of being the overlapping of two circles, it would really be the area in between two, where again the surface of the lens is formed by the arcs of the circle. So the shaded area in the middle on both of these pictures, that's the type of lenses that we're going to be studying in this chapter. These are both called double concave, double convex, meaning that they have the same shape on each side. Lenses do get a lot more complicated where they can have two different curvatures on each side, or one side could be flat, and that would give us some different effects, but we're not going to be looking at that in this chapter. So two types of lenses. Lenses can either be converging or diverging. So a converging lens is one that focuses parallel rays of light. So in this case, for this image, this would follow the rules of refraction that we studied last chapter. So all these parallel incoming rays of light, when they hit, if you were to sketch a normal here, then it would bend towards the normal as it goes into a slower medium, and away from the normal when it leaves and goes back into a faster medium. So following those rules, if you have parallel rays of light, they would focus at a focal point shown here on the other side. The distance from the center of the lens to that focal point is called the focal length. So there's those terms. For a convex lens, that distance of the focal length is considered positive. There are in this chapter a few sign conventions. When you hear the word sign convention, what that means is there's not necessarily a physical reason for a number having a positive or negative sign on it, but we all do it the same way and the same by rule so that our answers turn out the same, basically. There's a few different places in physics where that happens. If you were to completely flip the signs on everything, you would still get the same answer, but you need to have, in this case, the convex lenses will have a positive focal length and the concave lenses will have a negative focal length, so you have to keep that the same the whole time. So here's a diverging lens. The difference with a diverging lens is that it doesn't focus rays of light, and in fact it spreads rays of light. So again, you have the parallel light rays coming from the left, and where they focus together then would actually be on the left side of the lens. So these dotted lines are not actual rays of light, but they're traced back from these rays that continue through. So if you trace them back, you'll find that they all meet at one place, and that is the focal point. Again, this one has a focal length. Notice it's on the left side of the lens, and so in this case we're going to consider that to be a negative length. The nice way to look at this is assuming that your light is going from left to right in a diagram, you're going to say that, think about it like a number line, that the center of the lens would be 0, so anything to the right is positive and to the left is negative for the focal length. In last chapter, again, I mentioned that we did all the bending according to Snell's law. A nice thing that you'll like in this chapter is that instead of bending the light rays twice, we use what's called the thin lens approximation. The nice part about that is that the light rays are going to go through the lens exactly to the middle of the lens and just bend once. That approximation gives you the same answer as if you bent it twice going into and out of the lens. That line right straight up the middle of the lens is called the vertical axis, and I'll show you that on a diagram in a couple slides here. So same result. So that's a nice approximation. You don't really need to know that term other than just to understand that we do that in this chapter. Okay, as we look at images, the whole point of this chapter is to be able to describe the images that lenses and mirrors form. there are a couple different categories that we look at when we describe an image. An image can either be real or virtual. And the way the textbook definition here, a real image can be seen on a screen. A virtual image cannot be seen on a screen. And I think the easiest way to think about a virtual image is that if you look at yourself in the mirror, you know the light rays don't actually go through the mirror to where the image appears to be, because the image of you, if you look in a mirror, appears to be behind the mirror, and you know no light rays actually go there. So that's a virtual image. That's an easy way to think about it. In terms of the diagrams that we're going to be making, and another way that you can define real and virtual is to say for a real image, the light rays will actually intersect at that location. For a virtual image, again, think a mirror, the light rays do not actually intersect where the image is seen. So when you draw a diagram, if the light rays really go there, it's real. If you have to trace them back or something like that to find the image, like we did on the concave lens diagram a minute ago, then that would be a virtual image. So an image can either be real or virtual. That's one way that you can define it. Another way is to say it's either upright or inverted. That's pretty simple. And the last one is to describe its magnification. So you'll call it either enlarged or reduced. And I didn't actually put those words on this slide, but you'll see that those words used a lot. An image can be enlarged or reduced. And mathematically, we'll cover the mathematics later, but mathematically, if you get a magnification greater than 1, then you know the object is enlarged. If it's less than 1, it's smaller. Again, we'll do the math later, but it kind of made sense to put that together with the definition for magnification. So the biggest thing that we're doing actually in this video is to learn how to do light rays, how to do a ray diagram for lenses. So we're going to do that here in a second. You have all the ray rules on your notes packet. The simplest way to say them, this one is actually kind of written for lenses specifically, but in general, whether it's a lens or a mirror, you can draw 3 rays, and they can be summarized by saying parallel focal point parallel, and straight through the center. And how those words are applied depends on what kind of lens you're talking about or whether you're talking about a mirror. So we'll look at the mirrors on a different video, but for now, looking at this for lenses. What you're going to see are, to begin with, you're going to see this type of a problem. So you'll be given everything here that's in black, and then everything that's in green is just identifying what all those pieces mean. So the horizontal line through the center of the lens, that's called the principal axis. The objects that you'll be given on your initial worksheet are going to be arrows, and you'll like that because they're easy to draw. I will make you draw kind of weird things just for my own entertainment, and that's just kind of silly, but it's whatever the object is, you'll end up drawing that same thing for the image. So in this case, an arrow is nice and simple. The lens in this case was given. The vertical axis is just straight up and down through the exact center of the lens. On both sides, notice that you have a focal point, and you're going to be using both of them. I just have it labeled in one spot, but those are both focal points for the light. And then you have 2f. 2f is literally twice the focal length. The only reason that is there is because there's a certain effect when an object is exactly on 2f, it tells you something about the image. And I'm not going to tell you what that is now because I want you to draw the ray rules and figure it out. So those are the basic parts that you'll be given. Most of the time you're given something like this to draw on the first worksheet for sure. You can be given problems that are just word problems, and they don't give you any of this and they make you draw it all. That can be done. It's kind of a pain, but it's doable. So that's where we're beginning with the type of with the diagram that you'll be given. So here's how you apply it. So this would be a sample problem. And again, you should have this on your notes packet and you can draw along. So we're going to apply those 3 ray rules. Again, parallel focal point parallel, and straight through the center. So the first thing that I did is I drew that purple line, which is the vertical axis, straight up through the center of the lens. All those ray rules, when I say parallel focal point, the in-between parallel and focal point is the vertical axis. So that's where you're drawing the first ray to. So our first one is parallel. Again, see how it's parallel to the principal axis and it hits the vertical axis. That's where it ends. So parallel focal point. Now this is important. I know on this one I'm going to bend to this focal point because this is a converging lens, so I know that it's going to focus light. If this were a diverging lens, my parallel focal point would go parallel, and then I would line my ruler up with this focal point, and that would cause the line to shoot up this way where it spreads light. So you do have to know which type of lens you're talking about, and that tells you how to apply the ray rules. So parallel focal point. It's very important, by the way, that your parallel lines are actually parallel to the principal axis, that you actually hit the center of the vertical axis, and that you hit the middle of the focal point. If any of those things are off, it will change where your image is going to show up. So that actually is important. So the red one here, parallel focal point. The next one is focal point parallel. So I'm going to use my other focal point here. I'm going to draw a line from the top of the arrow through this focal point to the vertical axis. So there's my blue line. That's my focal point parallel. Again, focal point to the vertical axis, parallel beyond that. Really important to make sure that line is actually parallel. Now, if I stop right here, I know that anytime I have two non-parallel lines, I'm going to have an intersection somewhere. So I can say I already know that my image is going to be here. If you draw very carefully, you may be correct. However, if you are not good at drawing, or if you've made a mistake, your image will show up in the wrong place. This is why we do the third ray. The third ray is straight through the center. When I say the center, I mean from the top of the arrow to the center of the lens and passing straight through. Now, if you've drawn your ray diagram very carefully, all three of those will intersect in one spot. If you do not draw them carefully, or if you mess up one of the rules, you'll get this kind of Bermuda triangle thing here, and that tells you that you made a mistake. So that's why we do all three rays here. There are, by the way, different ray rules that you could use. Those are the three that I've chosen to include, and that's typical. So now, I started my ray diagram from the top of the arrow. I didn't have to. I could have started it from the middle or from somewhere else, but it makes most sense usually to choose the tallest point. So where my rays intersect on the other side, this will be the tip of the image. So tip of the object becomes tip of the image. The base of the object here was on the principal axis, so the base of my image will also be on the principal axis. So that's how I know where to draw my arrow. So I know that the height of the arrow is the distance between the principal axis and where they intersect. So that's something that's easily defined. The thickness is really just kind of eyeballed here. We're not really super concerned with that. I'm imagining if it's taller, it's probably thicker as well. Is that important? Not really. So really just going for the height of the arrow. Now that I know where my arrow is at, I can describe the image. So is it upright or inverted? I know that it's inverted, and the reason I know that is because, again, the base has to start on the principal axis, and the tip has to be where the lines intersect. That just forces it here to be inverted. Is it enlarged or reduced? In this case, it's enlarged. Again, I'm looking at the distance from the principal axis to the tip of the arrow on both the object and the image. So the image is bigger, so it's enlarged. Is it real or virtual? This is probably the most tricky. This one is going to be real. It's real because the light rays actually intersect here. I didn't have to trace any back in order to find it. So that is real. And I'll show you one next that's not going to be real for comparison's sake. Now, on this one, by the way, I didn't mention that this line doesn't actually hit the lens. That is traumatizing for some students. Don't worry about it. It's okay. You want to make it hit the vertical axis. Now, in reality, there's a near infinite number of light rays that you could draw between here and here, and they're all going to form the image, but they would follow a whole bunch of different rules, and we only want to have to deal with 3 rules. So you can just imagine that the vertical axis extends past the lens and use it, and that's totally fine, so don't worry about that at all. The last one that we're going to do is a concave lens. So exact same ray rules, but they'll be applied in a slightly different way. So same object, parallel focal point. Last time I bent the light through this focal point because I know that it was a converging lens that was going to focus light. This one I know is a diverging lens that's going to spread light. So I'm going to line up the line with this focal point and bend it away from from the center of this lens, so it's going to bend away. Now when I do that, I know that I'm not going to have any light rays that are going to come together on the right side of the lens. So what I do is I'm going to trace it back, because I know that concave lenses, and you'll experience this after you've done a few, they're going to make virtual images, and virtual images are going to show up on the left side of the lens. So there's my parallel focal point. Now I'm going to do focal point parallel. I already used that first focal point, so I'm going to use the one on the right side. So I'm going to go focal point. That blue line is pointed at this focal point. So if I were to continue that line, it would hit the focal point. But I'm not going to, because the rule is focal point and then parallel. So once it hits the vertical axis, it's going to bend parallel. Again, I trace it back, and I trace it back based on what happens on the right side of the lens. So when I trace that back, I'm tracing it back parallel. As you can see, those two dotted lines now intersect. Now we'll do my last line and see if they all meet. And due to the wonders of PowerPoint, they actually do meet on the left side of the lens. So I know my image is going to form on the left side of the lens, and it's right there. Ta-da! So now we have our object and we have our image, and all we have to do is describe it. So is this upright or inverted? It's upright. Again, the tip of the arrow is going to be where all the light rays meet, which is up here. The base is going to stay where it began at, which was the principal axis. So it has to be upright. Is it enlarged or reduced? Looks smaller to me, so it's reduced. And is it real or virtual? This one is going to be virtual. And the reason that it's virtual is because the light rays don't actually meet there. We had to trace them backwards to get to that point. So now I have the image fully described. All of these, if you didn't notice, these are qualitative. We will do them quantitatively as well. So that's it for lenses. The next thing that we'll do here is going to be mirrors. So I'll save that one for the next video. So after this video, you are able to do the first worksheet from the chapter, which should be posted online for you if you don't already have it. And I believe that is it.